So continuing our discussion of IMFAs, we need to hit on now the attractions between molecular substances. So there are three of them: dipole-dipole hydrogen bonding and London dispersion forces. These are all the types of attractions, like I said, that are considered van der Waals attractions. They occur between molecular substances. So we're going to start off with the dipole-dipole attraction and move from there. So polar molecules obviously have permanent dipoles. So they are like little magnets. They've got a positive end and a negative end. And those positive and negative ends can attract to the opposite charge of neighboring molecules, and this is what forms the dipole-dipole. So this produces stronger attractions than what you're going to see in molecules that form London forces. And so these molecular substances are more likely to be a liquid at the same temperature, where similar nonpolar molecules would be gases, or they're likely to be solids when nonpolar molecules are liquids. So all other masses and stuff being the same, a stronger interaction with a polar bond is going to make for stronger attractions. So here you have dipole-dipole attraction. Let's say we've got this polar molecule HCl. It's not ionic, remember, it's polar because you have two nonmetals bonded to each other. So you have the partial positive of the hydrogen and the partial negative of the chlorine, and they're in close proximity to each other. So notice they're going to line up so that the positive end is more towards the negative end and vice versa. So the IMFA, the dipole-dipole attraction, is going to be between the positive end of one molecule, the H of one molecule, and the chlorine of another molecule. And so you have all sorts of attractions going on. And this is what holds polar molecules together. All of these strong attractions that are permanently there make for things more likely to be harder, or things harder to break apart. Now, hydrogen bonding is a super strong kind of dipole attraction. Like we said before, it occurs between molecules that have hydrogen atom bonded directly to fluorine, directly to oxygen, or directly to nitrogen. And so what you wind up with is a very polar bond because of a few things. Hydrogen's really small, and these three atoms have the greatest electronegativities of all the elements. Fluorine's 4.0, oxygen and nitrogen are both 3.5. So you have the electrons being pulled really close to the oxygen or the nitrogen or the fluorine. This guy being small and positive is going to have a strong attraction to another oxygen somewhere on another molecule. And so you wind up with a really polar bond, which makes for a very strong attraction between molecules with those very polar bonds. So molecules containing hydrogen bonding have even higher melting points and boiling points than you would expect from polar molecules of the similar mass. So this is one thing that accounts for water's unique properties. You have all sorts of geological and biological systems on Earth that would be completely different if water didn't form hydrogen bonding. So we have to thank water that as humans we have water as a liquid on Earth because we're composed of a huge percentage of water. Because if you take a look, temperature versus molecular weight. Water boils at 100 degrees Celsius, whereas all of these smaller molecules will stay a liquid. Will be a gas at room temperature. So here's 0 degrees. So at 0 degrees, all of these things are already gases, but water stays a liquid until 100 degrees. That's a good thing because on Earth, temperature is somewhere up here on a normal basis as opposed to below the freezing point of water. So The reason that water does boil at such a high temperature is because of the hydrogen bonds. It takes a lot of energy to break those H's apart from the O's that are between different molecules. Like I said, nonpolar things, low melting points and boiling points, but water, super strong hydrogen bonding, much higher boiling point. So you got to be careful. These are the covalent bonds that we learned about in Unit 4A. These are where you have the sharing of electrons between this oxygen and this hydrogen. These are the hydrogen bonding IMFA attractions that we're talking about. This hydrogen has done nothing to overlap orbitals with this oxygen. It's just the fact that this is very positively charged and this is very negatively charged. And so you have a strong attraction between two opposite ends of the water molecule. Okay, these are the IMFAs. These are the covalent bonds. It's called a hydrogen bond, which is very misleading. It's really an IMFA. It's a hydrogen attraction. They need another name for it. And then the final thing that we're going to take a look at is London dispersion forces. Those are what's going to occur between nonpolar molecules. So in nonpolar molecules, you don't have a distinct positive or negative end. You have sharing of electrons reasonably equally so that the electrons aren't pulled one way or another. However, if you get atoms that are big enough, you can polarize bonds. They form what we call temporary dipoles because electrons are constantly moving. And so in a nonpolar molecule, you can still distort the electron cloud enough to get an attraction between the temporarily formed negative side of one molecule and the temporarily formed positive side of another. So it's kind of, the electrons are moving kind of like water sloshing in a shallow pan. You get the electrons sloshing back and forth, and when they do that, when they hit one side or the other, you get that temporary dipole generated. And so again, here we could have the electrons of one atom move to the side and be attracted to the nucleus of this helium. And so you wind up with a temporary polarity where this end is more positive, this end is more negative, this end is more negative, this end is more positive. And so you get this temporary attraction between molecules. It's temporary, it disappears. But within a big structure of a lot of these atoms or a lot of these molecules, you have London dispersion forces happening all the time. So, for example, what if we were to temporarily polarize this molecule due to random electron distribution? Okay, so you wind up with a positive end and a negative end. Well, what's going to happen? This positive end will start to attract the electrons of this molecule. So the electrons will kind of shift over here. So what happens? You get induced polarization of neighboring atoms. So now you have three atoms that are polarized, and you start to get an attraction. And once that happens, it's kind of like a domino effect. You induce polarization in everything else. So eventually you've polarized the entire structure because of the movement of the electrons within one molecule. And what happens when they go back? Well, this side's positive, this side's negative for now. Or it's the other way around, positive, negative, sorry. If something starts to move back, what happens? The polarization shifts, and you can get the electrons to slosh the other way. So in one case, they've sloshed to the left. Now in this case, they've sloshed to the right. So what are some of the consequences of having IMFAs? We've got melting points and boiling points that are going to increase as you get stronger IMFAs or as the molar mass goes up because of increased polarizability. So bigger atoms with more electrons or bigger molecules with more atoms are going to be more polarizable because of the electron's ability to slosh back and forth, like that word slosh. Substances are generally going to mix with substances that have similar IMFAs. So that phrase like dissolves like You may have heard it before, but it actually stands true. Similar things are going to interact with each other. So nonpolar things will mix well with other nonpolar things. Polar things will mix well with other polar things. Polar things will even mix well with ultrapolar things and ionic, because you have little pluses and minuses everywhere. Other physical properties, such as strength, conductivity, and so forth, are also related to IMFAs. We're going to do a bunch of activities that let you see those properties in action. So let's just summarize. You've got the strength listed over here on the left. We've seen this once before. These guys are pretty soft and brittle, easy to break apart because they're just very weak attractions. Metallic things are stronger, gives you a more malleable, ductile situation. These guys are hard but brittle because of the idea of shifting the ions if we put a force to it and breaking it apart. And then you have network, which is really covalent bonds holding all these atoms together, which winds up being very strong. Melting points and boiling points are going to increase as we go from the weak things to the strong IMFAs. And then in terms of conductivity, again, we're going to explore this a little bit more in the lab, but in terms of conductivity, molecular things do not conduct. Metallic things will conduct very well because of their delocalized electrons. Ionic things will conduct if you can get the ions free. So that means we either have to turn it into a liquid or we have to dissolve it in water. And typically, network things don't conduct electricity. All right, so how do you predict the type of IMFA a substance is going to form? We are going to create a flow chart, but we're going to do it actually in class together or in the third video because I'm going to end us here.